So welcome back. In this lecture, we shall discuss finite fields. In fact, we shall characterize finite fields. So this lecture is about characterization of finite fields. So characterizing 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 finite fields. So we shall make a characterization of finite fields in this lecture. So let us begin with this lemma. So we have a lemma 1, lemma 1. Let f be a finite field. Let f be a finite field containing containing a subfield. So if we have a finite field f that contains a subfield k, containing a subfield k with q elements, with q elements, then f has q raised to power m elements. Then f has q raised to power m elements, where where m is the degree of f over k, where m is nothing but the degree of f over k. Okay, so we are given a field f and its subfield, and we are given the cardinality of the subfield. Cardinality of the subfield k is q. Then we claim that the cardinality of larger field f is q raised to power m, where where q is the cardinality of k and m is the dimension of k and dimension of f as a vector space over k. Now see the proof. So we want to find the cardinality of the larger field f, and f is a vector space over k and it is a finite dimensional. F is a vector space over k and it is a finite dimensional, and it is finite dimensional. Of course it would be finite dimensional because f itself is finite, so it cannot be an infinite dimensional vector space over k. So it is finite dimensional since f is finite. Since f is finite. So denote this dimension by m. So let m equals dimension of f over k. So f has a basis over k consisting of m elements. That is, f has a basis over k consisting of m elements. Say the basis elements are say b1, b2, so on, bm. Okay, now let let V belongs to F be any arbitrary element, be any element. So you can write V as a linear combination of these basis elements. So then V is going to be K1 B1 plus K2 B2 plus so on plus Km Bm, Km Bm, where these Km they are from K, where Ki's, where K1 K2 so on Km they are in K. Now F is finite. Okay, so Ki they are coming from K, and there are q number of elements in this field K, because we are assuming that the cardinality of K is Q. So this means each Ki can take Q values. So you have Q choices for each Ki, and you have total M such Ks. So therefore you have Q raised to power M choices for each element. So any arbitrary element has Q raised to power M choices. So we are through then. Since each Ki belong to K can take Q values, can take Q values, and there are M such Ks, and there are M such Ks. So V has Q raised to power M choices. So V can be written in a Q raised to power M ways. Then V has Q raised to power M choices. So therefore V is chosen as any arbitrary element of F. So therefore we can say that F must have exactly Q raised to power M elements. Thus F must have Q raised to power M elements, and we are through. So if you have a finite field F containing a field K such that K has Q elements and M is the degree of F over K, then F has Q raised to power M elements. This is lemma 1. Now this lemma actually gives me the next theorem, which is very important, which says that a finite field has exactly P raised to power N elements, where P is the characteristic of F and N is the degree of F over its prime subfield. So we have theorem. So we have a theorem. So let F be a finite field. Let F be a finite field. Then F has P raised to power N elements. Then F has P raised to power M elements, where the prime P is the characteristic of F, where the prime P is the characteristic of F, is the characteristic of F, and N is the degree of F over its prime subfield, and N is the degree of F over its prime subfield. Prime. We know that the prime subfield of a field of characteristic P is isomorphic to this Fp which is Zp. This we shall use in the proof. Okay, so finite fields, they are cardinality having exactly p raised to power n, where p is the characteristic of f and n is the dimension of f over fp. Okay, this is n. So let us see the proof. Proof just follows from the previous lemma. Proof. Since f is finite, it so finite fields always have characteristic p. We know that the characteristic of a field is either 0 or a prime number. But once the field is finite, it cannot have zero characteristic. So finite fields always have characteristic a prime p. Since f is finite, it must have a characteristic p for some prime p. It must have a characteristic. It must have a characteristic. It must have a characteristic p for some prime p. For some prime p. And since we know that the prime subfield of a field of characteristic P is isomorphic to Fp, this is what I was saying. Since the prime subfield of a field of characteristic P is isomorphic to Fp, so it must have P number of elements. So contains P number of elements. So contains P elements. Okay, so you have a subfield of Fp. Say you have a subfield Fp of F, such that this Fp is P. Now you apply the previous lemma. By previous lemma, F must have P raised to power n elements. Then by previous lemma, F must have P raised to power n elements. So finite fields are having always cardinality of the form p raised to power n, where p is a prime and n is the dimension of f over fp, the prime subfield of f. So all finite fields must have prime power order. Okay, so thus all finite fields must have prime power order. Must have prime power order. Okay, so you can say that there is no field with 6 elements, or there is no field with 10 elements. Okay, so there is no finite field, there is no finite field with 6 elements, for example, because 6 is not a power of any prime. Okay, you cannot express 6 as a power of some prime. Then we have a question. We have seen that finite fields are so far. So as a remark, you can write this. So we have seen that in the above two results, we have seen that if f is a finite field, if f is a finite field, finite field, then cardinality of f is p raised to power n, where p is a prime number, and n is a positive integer. N is a positive integer. Now I want to see in the other way around. If you have a prime p and a positive integer n, does there exist a field of order p raised to power n? If we can answer this, then we have a complete characterization. We will say that finite fields are precisely of this form. Okay, so we have a question. So we have a question that does there exist a finite field of order p raised to power n? Does there exists a finite field with order finite field f such that this cardinality of f is p raised to power n for every prime p and every positive integer n? For every prime p and every positive integer n. Every positive integer, and this is my question and I want to answer this. In fact, the answer is positive. Okay, we can construct such fields. So let us answer this question. But before going to the main theorem of answering this question, we will prove some small lemmas. So I have lemma, so you call it lemma 3. Lemma 3. So it says that if f is a finite field with q elements, so if f is a finite field with q elements, so if f is a finite field with q elements, then for every a in f, every a in f has this property. It satisfies this equation. Every a in f satisfies this equation, a raised to power q equals a. So if the cardinality of f is q, then every element of f satisfies the equation a raised to power q equals a. Oh, it is straightforward. We will use some group theoretic argument. Now if a is 0, then this equation is clearly satisfied. Clearly a raised to power q equal to a is satisfied for a equal to 0. Is satisfied for a equal to 0. Now we are looking for non-zero elements. Now we know that the non-zero elements of a field form a group under multiplication. So the non-zero elements of f is a group, say f star under multiplication, under multiplication, and what is the order of this group? So the order of this F star is Q minus 1, and we know a well-known result from group theory. So if you have a finite group, we know that if G is a finite group, then A raised to power order of G is identity of G. Okay, for all A in G, for all A in G. Okay, so here the order is Q minus 1. So this means what? A raised to power Q minus 1 is 1 for all non-zero elements. Okay, so this actually also implies that A raised to power Q is A. So the lemma is true. So if F is a finite field with Q elements, then this equation is satisfied for all elements of F. Next we have another important lemma, lemma 4. So lemma 4, if F is a field with Q elements, if F is a field with Q elements, and K is a subfield of F, and K is a subfield of F, K is a subfield of F, then the polynomial, if I take this polynomial x raised to power Q minus x, okay, in Kx, factors in Fx in the following fashion: factors in Fx as a product of linear factors, as x raised to power Q minus x equals product x minus a. Okay, where a belongs to F, where a runs over F. So you can say that this polynomial x power Q minus x splits completely our F. And not only this, F is the smallest field with this property. So you can call F as the splitting field of this polynomial. And F is the splitting field, F is the splitting field of x raised to power Q minus x over K. Okay, so F is a field with Q elements. This is given to us. K is a subfield of. Now you choose this polynomials of this form. Then our claim is that F is the splitting field of such polynomials over K. Now see the proof. Now since the polynomial has degree Q, this polynomial has degree Q, so it has at most Q roots over F in F. Now since the polynomial since the polynomial x raised to power Q minus x has degree Q, it has at most Q roots in F. because any polynomial of degree n has at most n roots in the extension field. So f is the extension field of K here. So, so it has at most q roots in f. Q roots in f. By above lemma, but all the elements of f, they are roots of this polynomial, because we have seen that in the above lemma. See there, in the above lemma we have seen that if f is a field with q elements, then every element of f has this property, or you can say that here you can say that a raised to power q minus a is equal to 0 for all a. So means what? Means what? It actually means that a satisfies this polynomial x raised to power q minus x. So by previous lemma, every element of f is a root. By above lemma, by previous lemma, every element of f is a root of this polynomial. So all the elements of f, all the elements of f are roots of the polynomial, are roots of the polynomial, roots of the polynomial. And there are q of them, because it has cardinality q, and there are q of them. So what does it mean? It means that this polynomial splits over f. So thus the polynomial x raised to power q minus x is having this property, that it splits x minus a in f. So this means the polynomial splits, that is the polynomial splits over f, but it cannot split over a smaller field. Okay, because the smaller field would have fewer than q elements, and there won't be exactly it, uh, because it has the smaller field would have q number of elements, so the polynomial won't factor completely actually, and cannot split, and cannot split our sorry our sorry our a proper subfield of f containing k, containing k. Why? Because the smaller field would have fewer than q elements, as it would have fewer than q elements. So the polynomial won't have all the factors as linear. So we are through. Okay. So f is the splitting field of this polynomial. Now, getting all these lemmas in our hand, now we are ready to prove the actually, in fact, ready to answer the question that we posed in the beginning. So let me just state the theorem. So we have this theorem. It is called as existence and uniqueness of finite fields. So theorem 5. Theorem 5. Existence and uniqueness of finite fields. Finite fields. So statement for every prime p, for every prime p and every positive integer n, and every positive integer n, there exists a finite field with p raised to power n elements. There exists there exists a finite field a finite field with p raised to power n elements, and such fields are unique also. So any finite field with p raised and any finite field with q equals to p raised to power n elements is isomorphic to the splitting field of the polynomial to the splitting field of the polynomial x raised to power q minus x over fp. So once it is so, then we know that the splitting fields, they are unique. They are unique up to isomorphism. So such fields would also be unique up to isomorphism. Okay, so this is a very important theorem in finite field theory. It is a sort of characterization of finite fields. So for every prime p and every positive integer n, there exists a finite field with p raised to power n elements. And second part, any finite field of this type is actually a splitting field of polynomials of this form over fp, and from there the uniqueness would follow. So let us see the proof. First we will see the existence part. So proof. Okay, so let q equals p raised to power n, where p is a prime and n is a positive integer, where p is a prime and n is a positive integer. Our aim is to show that there exists a field of this order. So to show that there exists a field of order q, there exists a field of order q. Consider now this polynomial. Consider the polynomial x raised to power q minus x in fpx, and let f be the splitting field of this polynomial, and let f be the In fact, we would show that f is actually the required field. Let f be the splitting field of this polynomial, our fp. Okay, our fp. Okay, now what is the derivative of this polynomial? Now since the derivative of this polynomial, since the derivative is what is q x raised to power q minus 1 minus 1, and this polynomial is our fp, and fp has characteristic p. Okay, and q is p raised to power n, so in fp this would become 0, so you will get that this is minus 1. Okay, so it's a constant in fpx. So the derivative of this polynomial is a constant polynomial in fpx, so it has no root in fpx, and so has no root in fpx. So we know that therefore this polynomial is separable, or you can say that all the roots of this polynomial are distinct and there are few such roots. Okay, and so x raised to power q minus x has q distinct roots in f, has q distinct distinct roots in f, distinct roots in f. Okay, we will show that f has precisely q number of elements, that is the elements of f are precisely the roots of this polynomial. Okay, this is our job actually. Now let s be the collection of the roots of this polynomial in f. Let s be the this set a in f such that a raised to power q minus a equals 0. That is to say that the set of roots of the polynomial, the set of roots of the polynomial. Now our claim is that this S is a subfield of f. Our claim is that S is a subfield of f. So it has to be closed with respect to the operations of addition, multiplication, and inverse. So it would be a subfield. It should also contain the 0, and 0 is of course there because 0 satisfies this in this equation. So number 1, S contains 0 clearly. S contains 0, so it is clear. Number 2, now you choose any A and B in S. So let A comma B be in S. Then this means what? This means A raised to power Q minus A is 0 and B raised to power Q minus B is 0. So we have to show that A raised to power Q minus B raised. So we have to take the difference and show that it is also 0. So if I take A minus B raised to power Q minus AB, it is nothing but A raised to power Q minus B raised to power Q minus AB, because we have proven such a thing. We have proven that if characteristic of f is p, then we applied the binomial theorem to get this result. And here we also have the same thing. So by that result, okay, the same theorem where we prove that the Frobenius map a raised to power a goes to a raised to power p is a ring homomorphism, a homomorphism of fields, in fact. So by that result, so this is equal to 0. Okay, so this means what? This means a minus b also belongs to S. Third thing, if AB belong to S and B is not equal to